Hello everyone, welcome to this unit. In this video I'm going to talk about the Phonon calculations in material science using VASP and Phonopy. Phonons play a major role in many of the physical properties of condensed matter, such as thermal conductivity and electrical conductivity. The study of phonons is an important part of condensed matter physics. By listening to this unit, we will learn how to perform Phonon calculations in material science and then obtain thermal properties for our target systems using VASP and Phonopy. So let's get started. There are generally two main steps. The first step, as usual, is structure relaxation, and then the second step is Phonon calculation. In the first step, structure relaxation, we optimize our target structure and use the relaxed structure in concar file for the next step, so that we need to copy the concar file of the first step to the Pascal file of the second step as a relaxed structure. So in the first step, the only file that we need for the second step is the concar file, which is a relaxed structure. Well, let's start with optimization step. The structure I have here is a bulk layered material containing the transition metal chromium, shown here as dark blue, which is sandwich carbon atoms, and aluminum layers are between them. The structure type does not really matter for the Phonon calculations, and I just took this structure randomly. You can follow the process with what structure you have. Here you can see the unit cell from both side and top views. This is a side view and this is a top view of the structure. As you know and explained a couple of times in this channel, we need to apply proper in-car, K-points and podcar files for the relaxation of our structure, and I wouldn't like to repeat them here. You can see the previous videos and I explained them in detail. Here I use 18 grid points in X and Y directions and 6 grids in Z direction, based on the lattice parameter I have here in the unit cell. All the parameter you need to apply in in-car file is explained before, and here the only parameter that is very important for the Phonon calculation is ISIM. That should be equal to 1. I will explain the importance of this tag later on this tutorial. ISIM determines the way VASP treats symmetry, and ISIM equals 1 switch on the use of symmetry. Equilibrium crystal structures can be obtained by minimizing residual forces and optimizing stress tensors, as we already did in the first step. There are two main methods for the Phonon calculations. The first one is the Supercell method or finite difference method, and the second one is density functional perturbation theory, DFPT. When an atom in a crystal is displaced from its equilibrium position, the forces on all atoms in the crystal rise. Analysis of the forces associated with a systematic set of displacements provides a series of Phonon frequencies. First principles Phonon calculations with a finite difference method can be made in this way. So for the Phonon calculations using a finite difference method, we need to make a systematic set of atom displacement for obtaining the Phonon frequencies. An alternative approach for Phonon calculations is the density functional perturbation theory. I recommend finite difference method, and here I will explain only the Phonon calculations using finite difference method. DFPT or density functional perturbation theory will be explained in another video in this channel. For the Phonon calculations, we use VASP and Phonopy. For the ones who doesn't know Phonopy code, Phonopy is an open source package for Phonon calculations at harmonic and quasi-harmonic levels. And here I consider that you have already installed the Phonopy code in your computer. And if you haven't, you need first install this open source package. The procedure of installation is very easy and straightforward, and everything is explained in the website in this up here in the installation tab. And you could comment below if you have any problem for the installation, and I will try to reply very soon. As you can see here, Phonopy has many features, and for example, phonon band structure, phonon density of a state or partial density of a state, for example, phonon thermal properties such as free energy, heat capacity, and entropy, group velocities, and many others, and you can check in the website. Here in this unit, I will try to explain how to calculate the phonon band structure and density of states and also thermal properties. Well, we need first to create the proper supercell from the relaxed structure obtained in the first step. Lattice constants for the phonon calculations should be at least between 1 to 1.5 nanometers. The supercell can be created by Phonopy using this command in the directory of step 2. I decided to make 4 times 4 times 1 supercell in X, Y, and Z direction to fulfill the criteria of having lattice parameters at least 1 to 1.5 nanometer. Can create different supercell according to your structure, and the size of the supercell is very important to get the right phonon frequency. Well, after performing this command, you can see that some other files are created. The one is phonopy_disp.yaml that includes information about the structure, supercell, and displaced atoms. We do not need this file for the calculation, and we can just find information about the supercell and displaced atoms in this file. As you can see, 6 Pascal files are created: Pascal 1, 2, 3, 4, 5, and 6. These files contain single atomic displacements. You can visualize them, for example, using VESTA software to get and feel the concept of a single atomic displacement in a better way. In each of these files, one atom is displaced from its equilibrium position. The number of these files depends on the symmetry of your structure, and you could have less or more. As the symmetry of the structure is lower, you need more single atomic displacements. That is why I said it's recommended to turn symmetry on by isim equals 1 in the incar file of the optimization step. When you turn the symmetry on, VASP will treat symmetry and optimize the structure with higher symmetry. Then in this step, the number of required single atomic displacement will be less, and then less computation time is required for the phonon calculation. For example, if I hadn't used isim equals 1 in the optimization step, I would get more single atomic displacement here, more than 6. The other file is created here is spascar. Spascar is perfect supercell, and it uses for density functional perturbation theory, not finite difference method. And the only files that we need for finite difference method are Pascal 1, 2, 3, 4, 5, and 6 here. And it's quite dependent on your structure, as I said. And maybe you will get more than 6 single atomic displacement or less. Well, then we need to make 6 different folders for each single atomic displacement. I named these folders this 001 until this 006. You can name them whatever you like. and then place these Pascal files for each single displacement atoms to each of these folders one by one. Pascal 001 to this 001, and Pascal 2 to the second folder, and the last one to the last folder. Then rename these Pascal files to Pascal in each of these folders. Now we have one different Pascal file with one different atomic displacement in each of these folders. Here you can see the supercell that is created from both side and top views, and this is supercell from side view and the supercell from top view. Well, in each of these folders we need to perform only self-consistent calculations. So then after placing the Pascal files with different single atomic displacements in the folders, we use the same Pascal file as we use in the optimization step. Since we are dealing with a supercell now, we need to apply finer grid points in the K-point files. I use the 6 K-point grids in all the directions since 4 times 4 supercell is created in X and Y directions, and the lattice parameter in the Z direction is the same as the unit cell. That's why the K-point grid in Z direction remained fixed. Keep in mind that you need to apply the proper K-points according to your structure and the supercell you made. In the incar file, we need to set the parameters for self-consistent calculations. The important tags for the self-consistent calculation, as you know, is Iberion is equal to -1 and NSW equals to 0. I wouldn't like to explain the concept of these tags since I have explained them already a couple of times in the previous videos in this channel, and you can watch them if you need to know the physical meaning of these tags. Apart from the required tags for the self-consistent calculations, we need to pay attention to 3 tags for the Phonon calculations. The first one is LReal, that determines whether the projection operators are evaluated in real space or in reciprocal space. For the Phonon calculations, it's essential that the projection operators are evaluated in reciprocal space. Since the default of this tag in VASP is LReal equals to false, projection done in reciprocal space, I haven't sent this tag in the incar file, but if you apply the projection in real space, it's necessary to change it to reciprocal space. So it's necessary to have LReal equals to false or nothing, because the default is already false. The other one is add grid, that should be true. However, it doesn't seem to be essential, this tag, but doesn't cost much either. The other tag that is associated with the symmetry and for the Phonon calculations, we don't need to use symmetry, so we need to set iSym equals to 0. Here you can see the effect of the evaluation of the projection operators in reciprocal space. On top, the Phonon frequency are calculated while the projection operators are evaluated in real space. However, here the Phonon frequencies of the same structure are calculated while the projection operators are evaluated in reciprocal space. LReal is false. It means the projection are evaluated in reciprocal space. As can be seen, the Phonon frequencies are negative if the projections perform in real space. So it's necessary to take it into account that the projections must be evaluated in reciprocal space for the Phonon calculations by setting LReal equals to false in incar file. And as I said, this is the default of VASP. Well, after performing the self-consistent calculations for all the single atomic displacements, here displacement 1, 2, 3, 4, 5, and 6, the next step is creating the force sets. The only output file is required to create the force sets is the VASP run.xml in each of these displacement folders. To create the force sets, we need to use this command in the directory of step 2. F here is means force sets, and this displacement 001 is the name of the first folder, and the VASP run is which is created in the first folder, and then the second folder name and the VASP run that is created in the second folder until the last one, the name of the last folder and the VASP run which is created in the last folders. So using this command, we can combine all the VASP run which is created in each of these separate folders to create our force sets in this step 2. So as you can see, the force sets file is created, and now we can do post-processing after making the forces from the VASP run of each of these folders, the displacement, single atomic displacement folders. In the post-processing, force constants are calculated from the sets of forces, and a part of dynamical matrix is built from the force constants. And the phonon frequencies and the eigenvectors are calculated from the dynamical matrices with the specified Q points. I will talk about this concept later on this tutorial. After creating force sets, we can calculate the phonon density of a state. And the phonon density of a state is calculated by setting the file name. For example, here is mesh.conf. And the first line of this file is atom name, and I have here 3 elements: chromium, aluminum, and carbon. And the second line is dimensionality, is the dimension of the supercell I have here is 441, and the third line is grid points, which is 24, 24, and 48 in x, y, and z directions. And then we need to use this command in the directory that the force set is already exists. And the P is for means plot, and S means save. And the mesh.conf is the setting file name. So after typing this command, we can get the phonon density of a state, as you can see here. It's important to take into account that the number of grid points should be independent of the results. So we need to increase the number of grid points until the result is not changed. To calculate the thermal properties, we can use the same setting file as we already used for phonon density of a state, mesh.conf. But in the command in the directory that forces is already exists, we need to add T. T means thermal properties. So by performing this command in that directory, we can get the thermal properties and this plot. The horizontal axis is temperature, and the default is until 1000 Kelvin, and the red line is Helmholtz free energy, and the blue line is entropy, and the green line is heat capacity. So we can control the temperature with the Tmax and Tmin and Tstep tags in the setting file mesh.conf. So for example, we can control Tmax until 500 and Tmin with, for example, 200 until 500, and Tstep is default is 10 Kelvin, but we can control it, for example, 50 Kelvin or 1 Kelvin or whatever you like. And the concept of these values, as you know already, Helmholtz free energy is the lattice internal energy, U is lattice internal energy minus temperature times entropy. So as the temperature increases, entropy will be increased, and the Helmholtz free energy is decreased. But for solid, we have another term that is called vibrational internal energy. So in addition to the lattice internal energy, UL, which is calculated by DFT, we have another term that is called vibrational internal energy that is related to phonons. So using these thermal properties and this plot, we can calculate and we can have the vibrational internal energy in all the temperature range we already calculated and set in the mesh.conf. So all the values in this plot, Helmholtz free energy, entropy, and heat capacities, will be written to output file, which is thermal underlying properties.yaml. As you can see in the top, the unit is defined, temperature is Kelvin and other units. And here you can see that all the values will be written. For example, temperature is 0 Kelvin and the Helmholtz free energy at 0 Kelvin, and vibrational internal energy is the last one, and for other temperature as well, 10 Kelvin, 20 Kelvin, 30 Kelvin until the end. For example, as you can see here, for the 40 Kelvin, the Helmholtz free energy is 76.72, and the entropy, it will be written here, is 3.42, and the heat capacity as well. And the last one, the energy, is vibrational internal energy, which is 76.85. As you can see here, the vibrational internal energy is larger than Helmholtz free energy, because the temperature times entropy will be deducted from the vibrational internal energy. So always a Helmholtz free energy is less than the vibrational internal energy. Last but not least, the main objective of this unit and tutorial was the calculation of phonon band structure. In order to calculate the phonon band structure, we need to make a setting file first. The setting file, which is called here, for example, band.conf. The band, we need to create this band.conf first in the directory, and in the directory that the force sets is already exists. The first line of this band.conf or setting file is the atom name, which I have chromium, aluminum, and carbon. The second line is dimensionality is 441, and the primitive access is auto. And the next one is, which is very important, we need to define a proper k-path for our structure, and it depends on the type of our structure. So we need to find a proper k-path based on our structure and put it here. The next one is band points, the number of points between each pass, and 100 or 101 is a safe number, and then band connection. After creating this setting file and band, which is called here band.conf, we need to type this command in the directory that force sets and band.conf is already exists. Phonopy, P is print, and S is save, and the band.conf is this file which is already created. And then we can see this phonon band structures. So as you can see here, there is no imaginary or negative frequencies in the phonon band structures, and we can conclude that this structure is dynamically stable. But if you get the imaginary mode, you can increase your supercell you have already applied. For example, use bigger supercells and repeat the calculations. But if you get again the negative imaginary mode, it means that your structure is not stable dynamically. Uh, Basically, we can get more information from Phonon frequency of the structure. And but the main objective of this unit was how to calculate the phonon frequencies. And if there is no imaginary mode, it means that our structure is dynamically stable. In order to understand what kind of information can be obtained from the phonon frequencies, I will make another video and explain the physical meaning and the concept behind the phonon frequencies and how we can get more information from that. I would like to thank you for listening to this video, and I hope that I could explain how to calculate phonon density of a state and band structure as well as thermal properties using finite difference method by VASP and Phonopy. And this video would be helpful for you. Please comment here below or email to me your feedback and your questions, and I will try to answer them. Please subscribe to this channel and hit the bell icon to be notified the next video. And thank you again very much for listening.